All right, now annuities is a lot different than compound interest. Not a lot different, but there is a distinct difference. First of all, there's two types of annuities that we're going to do today. One, again, is investing, and the other is borrowing. Now, we looked at that in compound interest. In terms of our formula, it didn't matter because we used the same formula, but it was all about perspective. Are we earning the interest, or unfortunately having to pay the interest? With annuities, we're going to have two different formulas for the two different situations. So what we're going to start off with first is with investing. Now, again, here's the difference within annuities, is that you're making regular payments, right? With compound interest, we didn't do that. We either borrowed the money and waited and then paid it all back, or we invested the money, which is a good thing, waited and then got all the money back waited and then got all the money back. With annuities, things are different. You're constantly making payments. What we're going to do here is investing to start off. And at 10:30, we're going to look at probably something you're going to deal with more with in life, and that's borrowing, unfortunately, for a car, for a house, or for school in a couple of years. I know I definitely had to borrow money. Now, so again, first off here, we're looking at investing. So an annuity is used to invest, again, when you're making equal amount of payments. So generally what you're doing is you're making the same payment at a regular interval. So an example would be paying $50 at the end of every month. All right. That would be an example of an annuity. Now, here's the difference between a compound interest account and an annuity. Say if we're looking at the perspective of investing, is that with compound interest, again, you put the money in, you walk away, and that money is earning interest. And at the end, you collect it all. All right. You collect both your principal and all the interest that you added up. But with an annuity, it grows quicker, much, much quicker, because not only are you putting, you could start off with an amount, but you keep adding to the principal. You keep adding money. And so not only is your money in your account earning interest, but you're also bumping it up because you're bumping up the principal. So the interest is climbing and your principal is climbing at the same time. Whereas compound interest, your principal is the same essentially, and it's just making interest, right? So that is the big difference. Now, we have a new formula, like I said, and some of the variables are some of our regular ones that we've dealt with. For instance, R, which is going to be our annual or our interest rate. Always given to you as annual, and that's sometimes where we have to make adjustments. And is the number of, well, it can be looked at two different ways: the number of compounding periods or the number of times that you're putting money into the account. Now, here's our two new variables here, FV and R. Now, FV is only, and I hate, the textbook does this because I hate having two letters, which only means one value. And the FV stands for future value, what it is going to be worth when you're done making those regular payments and also gaining interest. And R stands for those are the regular payments. All right, so there is our annuity formula for investing. Again, we're going to have two different formulas, one for investing and one for borrowing, which didn't have with compound interest. And so if I get to the first example here, it says, how much will accumulate, future value, in an account in which $100 is placed in the account after every year for 20 years at an interest rate of 8% compounded annually. All right, so like I did before, which I'm a big fan of in any math class, is I'm going to write out what information I know. So I've got four variables here. And again, I know that I'm going to use this formula. That's a part of the trick here with tests and quizzes, well, I guess tests for us, is that what formula do I use? It's easy day to day, but when they're all mixed together, it's like, which one do I use? Here we're having investing and we're putting in money at regular intervals. So that's when you know to use this formula here. And so I need four variables here. I got my future value, my regular payment, the number of, we'll go with the interest rate, and then the number of compounding periods or the number of payments. Could work either way, same thing. So now I go back to my question. I'm going to read it again because I'm terrible at English. It's early in the morning and, well, I know what I'm getting into here. So it says, how much will accumulate? Now that used to be in our compound interest formula. That would be our A. But in here, because it's an annuity formula, that's our future value. I wish the textbook could put it, eh? It's the same thing. Now, in an account in which $100 is placed into account after every year, well, $100 would be considered our regular payment. Now, the interest rate, it says 8% compounded annually. And so because we're making annual payments, I don't have to do anything to this interest rate other than, again, converting the percent to a decimal. Because, again, percent is useless in a math formula. You have to convert it to a decimal. So 8%, and if I divide it by 100%, I get 0.08. Now, N is the number of payments or the number of compounding periods. Same thing. Now, we are making a payment for 20 years at the end of every year. So in total, we're going to make 20 payments. All right, so now I have my variables. So what I'm going to do now is substitute into my annuity formula here. And so I have my FV is equal to, again, my regular payment is 100. Big square brackets here because I have brackets within brackets. That's why I go with the square brackets. I see here I have 1 plus the interest rate. So I'm going to go 1.08 because my interest rate is 0.08. And the number of compounding periods, we're going to, it's going to be compounded 20 times because we're going to make that many payments. And then I got my minus 1 here. And then, of course, down at the bottom, this is what a lot of students forget. Most common mistake with this formula is don't forget about the little r down there in the bottom. Now, it is just the interest rate. That's another thing that people get confused on. In the brackets here, it's 1 plus the interest rate, but in the denominator here, it's just the interest rate. So we get 0.08. All right, now to find our future value, all we're doing is follow embedments here. So I go right to the brackets. And in fact, inside the brackets, I have brackets. So I got to work on that with that exponent there. So I have my future value is equal to 100. Let's go with the square brackets here again. I got that minus 1 all over. Hopefully I don't run out of room here. 0.08. I take 1.08 to the power of 20. And let's see here. I'm getting 4.661 or 4.66. All right, now again, continuing on with bedmas. I'm going to subtract here in the square brackets. Future value, 100 in the square brackets. Well, it doesn't have to be square brackets now. Well, 4.661 minus 1 is 3.661 divided by 0.08. All right, and then this, of course, can just be easily calculated. Multiply 100 times 3.661 divided by 0.08, and I get $4,576. And don't forget, because we're in math here, we don't want to miss out on that 25 cents. So when you look at it in this case, just from a math view, if we're making $100 payments for 20 years at the end of every year, 20 times 100 is just $2,000. But because it's an annuity, you end up with quite a bit of money because, again, you're the principal. You start off with $100, then it's 200, then it's 300, but then the interest keeps adding up for you a lot quicker. So in the end, even though we put $2,000 in the bank, you end up with $4,576.25. All right, let's try another one of those because that was the easier one with just annual. But of course, that's not how it always works. So I'm going to leave my formula up there because, again, I don't have a very good memory. So that's why I give you a formula sheet because I need one too. And in real life, you would definitely be able to find the formula. All right, now, see here, we get to example 2. All right, so it says, let's see here, example 2. How much has accumulated in an account if $10 is placed in the account each week for 2 years at a rate of 9% compounded weekly? So again, here's a situation. We're continually putting money into the bank, right? So it is, again, an annuity, of course, because that's what we're doing today. All right, so again, I'm gonna write down my 4 variables here. So we got FV, there's my future value. I got my R, and I got my little r, which is the rate, and my N. All right, now again, I like to reread these things. So how much has accumulated in an account? Right away, that's telling me I am looking for my future value here. All right, if $10 is placed into an account each week for 2 years, so our regular payment is $10 each week. So let's just cut into Tim Hortons there. Not too bad to do. Now for 2 years, 2 years. So that's our end value. We'll come back to that. It's 9% compounded weekly. All right. So again, when we're looking at our rate, it's 9% compounded weekly. So the 9%, again, I'm going to convert to a decimal, 0.09. Again, that's dividing by 100%. But because this is compounded weekly, we gotta change our interest rate to a weekly interest rate. And hopefully by now, you know that there are 52 weeks in a year. And so I take my 0.09 and I divide it by 52. And I'm getting, let me see, down to my first 2 non-zero numbers. I get 0.0017, real small number, because it's a weekly interest rate. All right, now we get to the number of compounding periods, or the number of payments we're going to make. We're going to make weekly payments for 2 years. So for 2 years times 52 times, because there's 52 weeks in a year, which, well, 2 times 52, our end value is going to be 104. We're going to make 104 payments here. All right, so now I've got all my variables. All right, so now I'm going to substitute in. So there's my future value. Regular payment here is 10. So put that in there. All right, little square brackets because I have brackets within brackets. 1 plus r's, that's in brackets. All right, so I got 1 plus this thing. Well, then that means I got 1.0017. My exponent is n, which is 104. And of course, the minus 1. And again, don't forget the denominator. I don't know how many people always do that. They're like, why is my number so small? Well, it's because you forgot to divide by, in this case, it would be 0.0017. All right, so now I got everything substituted in. It's just bedness. Heading to the brackets again. So I'm going to do my 1.0017 to the power of 104. It's definitely a calculator job. All right, and so I take 1.007 to the power of 4, and I get 1.197 minus 1. There's that minus 1 there. Oh, and again, can't forget to divide by my rate. All right, so again, continuing on with bedmas, I head to the brackets here. All right, so, well, 1.197 minus 1 is just going to be 0.197. And again, divided by my 0.0017. And let's see here. So if we have to cut out Timmy's, $10 a week, roughly that's 5 double doubles, Monday to Friday, large double doubles. Let's see here. You would end up with, so fast things add up, $1,138.38. There we go. So if somebody cut out Timmy's for 2 years, getting their large double double, there we go. Because a large double double is exactly $2. 2 times 5, you'd end up with $1,138. All right, so let's try. Well, I get one more here because this formula doesn't get too crazy on us, other than substituting in. Our formula there. All right, so we get to, fix my little R there. There we go. All right, so we get to example number 3. All right, so let's check it out. It's our last one. If Sandra makes a $7,000 down payment on a $25,000 car and ends up financing the rest over 2 years at a rate of 8% compounded monthly, what will her monthly car payment be? All right, so she wants to keep making payments so that she can pay off the car. So $7,000 down and on a $25,000 car. So she wants to invest money to buy this car. Now she's got $7,000. All right, so again, she's investing money to buy this car. Now, future value. Here's our regular payment. And let's see what else we got here. We got our interest rate and the number of payments. Now she knows that this car is worth $25,000, but she's already saved up $7,000. Good for her. That's quite a bit of money. So what she needs in terms of her future value here, it's a little bit of work. It's a $25,000 car, but she's paying off $7,000, which can happen. You make a down payment. And so that means in the end here, she needs $18,000 to buy this car. All right. Well, what would her monthly car payment be? That's our regular payment to invest. She didn't borrow this money. She's saving up for it. All right. Now, it says ends up finding the rest over 2 years at a rate of 8% compounded monthly. So again, our rate, it's 8%. So again, I'm going to divide by 100% here. So it's 0.08. But again, I have to convert that to a monthly interest rate, right? So I have to divide by 12 because there's 12 months in a year. All right. And let's see here. We end up with 0.0 going to the first two non-zero numbers here, 0.0067. All right, now she is saving up for this car. Let me see here. For 2 years. 2 years. She's going to make payments for 2 years, but she's making monthly payments. So 2 years times 12, because 12 months in a year, we have 24 in total. All right, so let me see here. We got our this. All right, we have all our variables but one. All right, so here we go. I'm going to substitute in, but this time I have my future value. We're saving up $18,000. All right, so we need to save up. She already had $7,000. The regular payments, that's what we're trying to find. So put an R in there. Again, we got our square brackets. 1 plus R. Well, there's our R, so we're going to have a 1.0067. To the power of n, which is 24. Minus 1 there. And of course, I cannot forget our interest rate in the bottom, which is the 0.0067. All right, so just like before, I'm going to have to do some bedness, maybe a little bit of difference at the end here. So I have 18,000 equals R, and again, I'm going to do my brackets, so I got to take my exponent there. 1.0067 to the power of 24. I type that in. I get 1.1738. Oh, and again, I have my minus 1 there. Make that a nice 1. There we go. And of course, I have to divide by the 0.0067. Okay, so again, just kind of doing the math. Let's see here. So 18,000 equals R. Well, I can figure out what that is right there. 1.1738 minus 1. Well, I'm just going to end up with that 0.1738. And again, divided by 0.0067. There we go. Now, this is where I find, after all of this, that a lot of students have trouble with finishing this off. They get a little stuck here. Well, all I'm going to do is put these two numbers together because it's a division. I have a numerator and I have a denominator. So I can take that 0.1738 and divide it by the 0.0067. So I'm running out of room here though, but 18,000 here is equal to R. Again, I'm going to have some number there. So I take that decimal divided by a much smaller decimal, and I'm actually getting a nice number, relatively nice number, 25.94. So again, I just combined those two numbers by division. And then lastly, I'm getting R by itself. Well, this is my numerical coefficient here, this 25.94. So I'm going to divide both sides by 25.94. And those divide each other out. And my regular payments, whatever 18,000 divided by 25.94 is, and well, the regular payments, hope she has a good job, $693.91. And there we go. So that's if Sandra wants to save up for a $25,000 car. Well, she can. Well, she's got $7,000 in the bank, so she needs to save up 18 grand, and her regular payment will be $693.91. And that is the start of annuities. The first half, again, there's two halves to this. There's investing, and then which at 10:30 we're going to get more into borrowing, which is the most common thing when you're your age or even my age. You start off investing or borrowing money for a car, and then you move on to a house eventually is generally what happens.